This week in Environmental Science, we're going to take a look at Chapter 15, Non-Renewable Energy Sources, their impacts, and energy conservation. Our learning objectives for the chapter are the following. This lecture will help us understand our energy sources, the value of the EROI concept, coal, natural gas, and oil use, depletion of oil supplies, new fossil fuel sources, environmental, political, social, and economic impacts of fossil fuel use, energy conservation and efficiency, and nuclear power. In our central case study for the chapter, we take a look at the concept of hydrofracking the Marcellus Shale. This took place in a town called Dimmock in rural Pennsylvania. There's 1,500 residents there, and they were very happy to sign some contracts with a corporation called cont'd. Cont'd would pay them royalties on the sales of the gases extracted from their property. Soon after, the town experienced economic gains as there was money coming in and jobs for many people. Despite the economic gains, though, many of the residents were having some second thoughts. Their once peaceful community was changing. A lot of heavy truck traffic and even toxic wastewater spills were occurring. Then, some people's drinking water began to turn brown and gray and cloudy with sediment, and a strange chemical smell began wafting from their wells. On one of the days, New Year's Day 2009, one community member's well actually exploded from methane that had built up in her well water, and a spark from a motorized pump nearby set off the blast. Residents blame the drilling technique that Cabot Oil and Gas was using. It's called hydraulic fracturing, also known as hydrofracking and fracking. This is the drilling deep into the earth and then angling the drill horizontally once it meets a shale formation. Then electric charges create fractures in the shale. Then a slurry of water and sand and chemicals is pumped in. The sand lodges into the fractures and holds them open, and some of the liquid returns to the surface, including the natural gas that's stored there in the shale. A school teacher from the town went to local political leaders but didn't get anywhere with them. She also went to the Pennsylvania Department of Environmental Protection, but was turned away by them as well. Finally, she went to the news media, and the story got out, and documentary filmmaker Josh Fox came to town and filmed residents actually setting their methane-contaminated water on fire. His 2010 film, Gasland, won numerous awards, and Dimmock became ground zero in the burgeoning national debate over hydrofracking. In the United States, virtually all easily accessible oil and natural gas has already been extracted. So to extract more, we've had to come up with new technologies to go deeper and get sources that have lower concentrations. In formations like the Marcellus Shale, the natural gas is locked up in tiny bubbles and dispersed throughout the shale rock. This technique of hydraulic fracturing is making the shale gas accessible. This shale gas, this natural gas, is cleaner burning than coal and releases fewer of the greenhouse gases that other emissions lead to. For all those reasons, and also because of the powerful political influence of oil and gas corporations, policymakers have actually encouraged fracking and have freed it from many of the regulations and constraints that would normally apply. Fracking has been exempted from 7 major federal environmental laws that protect public health, including the National Environmental Policy Act and the Safe Drinking Water Act. As a result, gas companies don't need to report the chemical additives that they use in fracking, and they don't have to test for chemical compounds drawn up in the fracking wastewater. And I'll have you know that some of that wastewater is actually radioactive because drillers add radioisotopes, and sometimes radioisotopes that are trapped underground actually are released as well. Regulators, policymakers, scientists, and homeowners do not have access to data to make fully informed judgments about potential health or environmental effects of fracking. In such a climate of uncertainty, people in places like Dimmock are left to wonder and worry and argue. The school teacher and several dozen other families in town eventually brought lawsuits against Cabot, but some of their neighbors were angry with them. Those were the ones that had not had their water affected by the fracking. And there were many that felt that the benefits of receiving the money from the gas payments outweigh the health risks from pollution. After recognizing that for some Dimmock families the water was undrinkable, the Pennsylvania Department of Environmental Protection eventually fined Cabot and required it to pay for clean drinking water to be hauled in. However, Pennsylvania Governor Tom Corbett, an avid supporter of fracking, soon ordered an end to the water shipments. As publicity built and activists complained that Pennsylvania was not safeguarding its citizens, the U.S. Environmental Protection Agency stepped in, and federal researchers ran tests of Dimmock's water. Results showed elevated levels of several chemicals that could threaten health in 5 out of 64 wells tested. But the EPA said that Cabot was addressing these impacts. A lot of people, residents, and scientists there suspected that industry and politicians influenced the EPA's conclusion. The EPA denied such influence and embarked on a nationwide study of the health and environmental impacts of hydraulic fracturing, which was due out in late 2014. State governments have approached hydraulic fracturing in various ways. For instance, Pennsylvania's political leaders welcomed the gas industry with open arms, exempting them from regulations. New York's leaders placed a moratorium on fracking until further studies were conducted. Ohio, Texas, Louisiana, Wyoming, Dakotas, and others encourage fracking. Vermont has banned it, and California is still debating the issue, concerned about drought conditions and the fact that fracking requires large amounts of water. Today, many policymakers and scientists and engineers are seeking ways to minimize the impacts of hydrofracking. Humanity has devised many ways to harness the various forms of energy available on the planet. We've taken most of our energy from non-renewable sources, like fossil fuels and nuclear power, but we also have available to us a diversity of renewable resources. Of all the energy sources, though, we rely the most on fossil fuels. These are the highly combustible substances formed underground over millions of years from the buried remains of ancient organisms. We use 3 main fossil fuels in the form of solid coal, liquid oil, and natural gas. Fossil fuels provide most of the energy that we buy, sell, and consume because of their high energy content that makes them so efficient to ship, store, and burn. A single gallon of oil contains as much energy as a person would expend in nearly 600 hours of human labor. We use fossil fuels for transportation, heating, cooking, and also to generate electricity, which is a secondary form of energy that we can actually transfer over long distances and apply to new uses. Global consumption of coal, oil, and natural gas is now at its highest level ever. Across the world today, over 80% of our energy and 2/3 of our electricity come from coal, oil, and natural gas. Given our accelerating consumption, we risk using up our non-renewable fuel sources. Once depleted, non-renewable energy sources cannot be renewed, and that would include oil, coal, and natural gas. At current rates of consumption, we'll use up the Earth's easily accessible fossil fuels in just decades. This is why fossil fuel companies have developed other approaches like hydraulic fracturing to exploit less accessible deposits. And this is also why measures to conserve energy and improve energy efficiency are also very vital. There's also called stores of renewable energy. These are energy supplies that are not depleted by our use. They include sunlight and geothermal energy and tidal energy. Energy is unevenly distributed. Some areas of the globe have substantial reserves of oil, coal, and natural gas, whereas others have very few. Half of the world's proven reserves of crude oil lie in the Middle East, and the Middle East is also rich in natural gas, as is Russia. The U.S. possesses the most coal of any nation. It actually takes energy to make energy, though. We don't get it for free. To harness, extract, process, and deliver energy, it requires substantial inputs. We also have to use powerful machinery, vehicles, storage tanks, and pipelines, which costs a lot of money. All of that also requires huge amounts of energy. Net energy is the difference between the cost in energy invested and the benefits in energy received. So net energy equals energy returned minus energy invested. When we assess energy sources, it's also useful to use a ratio known as EROI, or energy returned on investment. EROI ratios are calculated like this. EROI equals energy returned over energy invested. Higher EROI ratios mean that we receive more energy from each unit of energy that we invest. Fossil fuels are widely used because their EROI ratios have historically been high. However, EROI ratios can change over time. Ratios rise as technologies to extract and process fuels become more efficient, and they fall as resources are depleted and become harder to extract. EROI ratios for producing conventional oil and natural gas in the U.S. declined from roughly 30 to 1 in the 1950s to about 11 to 1 today. This means we used to gain 30 units of energy for every 1 unit of energy expended, but now we gain only 11. EROI ratios for oil and gas declined because we extracted the easiest deposits first, and now must work harder to extract the remaining amounts. Speaking of fossil fuels, where do they come from? Well, fossil fuels are formed from ancient organic matter. Fossil fuels were formed from organisms that lived 100 to 500 million years ago. In order to form, they must be broken down in an anaerobic environment. An anaerobic environment is one with little or no oxygen. Such environments include the bottoms of lakes and swamps and shallow seas. The fossil fuels we burn today in our vehicles, our homes, industries, and power plants were formed from the tissues of organisms that lived that long ago. When the organisms died, they were buried quickly in an anaerobic sediment after death, and chemical energy in their tissues became concentrated as the tissues decomposed, and their hydrocarbon compounds were altered and compressed. Because fossil fuels form only under those certain conditions, they occur in isolated deposits. For example, the Marcellus Shale holds rich reserves of natural gas that other nearby rock formations do not. Geologists are searching for fossil fuels, and they drill cores and conduct ground, air, and seismic surveys so that they can map underground rock formations and predict where fossil fuel deposits might occur. The world's most abundant fossil fuel is coal, a hard, blackish substance formed from organic matter, generally woody plant material, that have been compressed under very high pressure, creating dense solid carbon structures. Coal typically results when water is squeezed out of such material as pressure and heat increase over time, and when little decomposition takes place. The proliferation 300 to 400 million years ago of swamps where organic material was buried created coal deposits in many regions of the world. To extract coal, we use strip mining for the deposits that are near the surface, subsurface mining for the ones that are deep underground, and mountaintop removal, where again, entire mountaintops are cut off. Remember, this is a very environmentally destructive process and has been very common in the Appalachian Mountains in the United States. The sludge-like liquid we know as oil or crude oil contains a mix of various hydrocarbon molecules. Remember, hydrocarbons are long chains of carbons bonded to hydrogen. If you go back to your chemistry chapter. Oil is also known as petroleum, although this term is commonly used to refer to oil and natural gas collectively. Natural gas is a gas consisting of methane, which is also known as CH4. Both oil and natural gas are formed from organic material, especially dead plankton, that drifted down through coastal marine waters millions of years ago and was buried in sediments on the ocean floor. Then the organic material was transformed by time, heat, and pressure into today's natural gas and crude oil. Two processes give rise to natural gas. Biogenic gas is created at shallow depths by anaerobic decomposition of organic matter by bacteria. You may smell this gas when stepping into the muck of a swamp. One source of biogenic natural gas is the decay process in landfills, and landfill operators are now capturing this gas to sell as fuel. Thermogenic gas results from the compression and heat deep underground. It may form directly or from coal or oil altered by heating. Most gas extracted commercially is thermogenic, and it's found above deposits of oil or in seams of coal, so it's often extracted along with those fuels. Underground pressure tends to drive oil and natural gas upward through cracks and fissures in porous rock until they become trapped under a dense, impermeable rock layer. Oil and gas companies employ geologists to study rock formations to identify promising locations. Once such a location is identified, a company typically conducts exploratory drilling. That's drilling small holes to great depths. If enough oil or gas is encountered, extraction may begin. Because these are under pressure while in the ground, they rise to the surface when a deposit is tapped. Once the pressure is relieved and some portions risen to the surface, the remainder will need to be pumped out. There are some unconventional fossil fuels. Besides the three conventional ones, coal, oil, and natural gas, other types of fossil fuels exist, and they're called unconventional. These examples of unconventional fossil fuels are oil sands, oil shale, and methane hydrate. Oil sands, also called tar sands, consist of moist sand and clay containing 1 to 20% bitumen. That's a thick and heavy form of petroleum. Oil sands represent crude oil deposits degraded and chemically altered by water erosion and bacterial composition. Oil sands are extracted by two main methods. For deposits near the surface, they use strip mining. They can also use deep underground extractions for the ones buried deeper. A second type of unconventional fossil fuel is oil shale. Oil shale is a sedimentary rock filled with organic matter that can be processed to produce a liquid form of petroleum called shale oil. Oil shale is removed by the same processes that form crude oil, but occurs when the organic matter was not buried deeply enough or subjected to enough heat and pressure to form oil. Oil shale is extracted using strip mines or subsurface mines. It can be burned directly like coal. Another way to process it is to bake it in the presence of hydrogen and in the absence of air to extract liquid petroleum. That's a process called pyrolysis. The world's known deposits of oil shale may contain 3 trillion barrels of petroleum, more than all the world's conventional crude oil, but oil shale is costly to extract and its EROI is low, ranging from a 4 to 1 down to just a 1 to 1. The third unconventional fossil fuel is methane hydrate, also known as methane, clathrate, or methane ice. It's an ice-like solid consisting of molecules of methane embedded in a crystal solid consisting of molecules of methane embedded in a crystal lattice of water molecules. Methane hydrate occurs in sediments in the Arctic and on the seafloor because it's stable at temperature and pressure conditions that are found there. Scientists estimate there's an enormous amount of this substance on Earth, holding perhaps twice as much carbon as all the known deposits of oil, coal, and natural gas combined. Japan recently extracted methane hydrate from the seafloor by sending down a pipe and lowering pressure within it, so that the methane turned to gas and rose to the surface. However, we don't yet really know whether extraction is safe or reliable. Scientists fear that extraction could release large amounts of methane, which we already know is a greenhouse gas that could also lead to landslides and tsunamis. Economics determines how much will actually be extracted. Technology limits how much can be extracted, and economics limits how much will be extracted. Extraction gets harder and more costly as oil or gas is removed. We remove the easy stuff first and have to drill deeper to get the rest and spend more money and use more technology to get the rest. The amount of economically recoverable oil and gas is based on the price of fuel. At higher prices, economically recoverable amounts approach technically recoverable amounts. The amount of fossil fuel that's technologically and economically feasible to remove under current conditions is termed its proven recoverable reserve. Here's a chart showing the amounts of fossil fuel produced and consumed by different countries. Refining produces a diversity of fuels. Once extracted, the oil has to then be refined, and the hydrocarbons within it are sorted out for different uses. Oil is used for fuel, lubricating oils, asphalts, and precursors of plastics and petrochemical products. Coal has been used for thousands of years to cook, heat homes, and fire pottery. Used on coal-fired steam engine, power factories, train ships, and industrial furnaces. And coal-fired power plants convert water to steam, which turns a turbine to create electricity for us. Natural gas is used to generate electricity in power plants and to heat and to cook in homes. Liquefied natural gas, also known as LNG, is gas that's been converted to a liquid and then can be shipped in refrigerated tankers. It's versatile and clean burning. It emits half as much CO2 as coal and 2/3 as much CO2 as oil. Oil is used to fuel vehicles, used as gasoline and diesel and jet fuel. Petroleum-based products from oil include lubricants, fabrics, and pharmaceuticals. Here's a diagram showing how fossil fuels are key in our everyday lives, from brushing our teeth to traveling to work. We're depleting our fossil fuel reserves, unfortunately. We've used half of our oil reserves. That's 1.1 trillion barrels. And remember, fossil fuels are non-renewable. To estimate how long this remaining oil will last, analysts calculate the reserves to production ratio, or the RP ratio, by dividing the amount of remaining reserves by the annual rate of production, which includes extraction and processing. At the current levels of production, which is 31 billion barrels globally per year, 1.7 trillion barrels would last about 53 more years. Applying the RP ratio to natural gas, we find that the world's proven reserves of this resource would last 55 more years. For coal, they estimate 113 years. But remember, these numbers could be off. We could actually have these last longer if we increase our efficiency and technology and our ability to conserve. Then again, maybe they won't last as long if we need to produce more. Eventually, however, production of any non-renewable resource will come to a peak and then decline, and general production tends to decline once reserves are depleted halfway. If demand for the resource holds steady or rises, while production declines, a shortage will result. With oil, this scenario has come to be nicknamed peak oil, because we've already used roughly half of Earth's conventional oil reserves. Many experts calculate that a peak oil crisis will begin soon. Geologist M. King Hubbard predicted that U.S. oil production would peak around 1970, and his prediction was accurate, and U.S. production continues to fall. Discoveries of new oil fields peaked 30 years ago, and we're using more oil than we're discovering. We won't recognize that we've passed peak production until several years have passed. Companies and governments don't reveal their true amount of oil supplies. Most estimates say oil will peak before 2040, and peak production will occur, and it'll have a momentous economic, social, and political consequence, and our lives will be profoundly affected. Writer James Howard Kunstler has sketched a frightening scenario of our post-peak world during what he calls the long emergency. Lacking cheap oil with which to transport goods long distances, today's globalized economy would collapse into isolated local economies. Large cities would need to run urban farms to feed their residents, and with less mechanized farming and fewer petroleum-based fertilizers and pesticides, we might feed only a fraction of the world's 7 billion people. The American suburbs would be hit particularly hard because of their dependence on the automobile. More optimistic observers argue that, as oil supplies dwindle, rising prices will create powerful incentives for businesses, governments, and individuals to conserve energy and to develop alternative energy sources, and that this will save us from these major disruptions. Mountaintop removal mining has brought coal extraction to a whole new level. The massive scale, it makes mining economically efficient, and it's safer than subsurface mining. There's fewer accidents and fewer health risks. However, it can cause staggering volumes of rock and soil to slide down slope. It can destroy entire hillsides and pollute waterways and destroy a lot of habitat. And sulfuric acid forms when rainwater and oxygen react with newly exposed rock containing sulfide minerals. And coal dust pollution also occurs along the transport routes. Oil and gas are under pressure and often rise to the surface, and the drilling reduces the pressure, so then the oil is harder to extract. Primary extraction is the initial extraction of available oil and gas. Secondary extraction actually produces more fuel. It includes solvent, water, and steam that's used to remove additional oil. And then fracturing breaks the rocks to release the gas, and we still lack the technology to remove every little bit of oil. Drilling requires lands, roads, and infrastructure, like housing. It pollutes soil and water and fragments habitats, and leaves toxic sludge behind stored in ponds. Directional drilling is when wells are drilled away from a drilling pad and require fewer pads. Hydraulic fracturing expands our access to oil and gas, unlocking formerly inaccessible deposits of shale gas and tight oil, and hydrofracking has ignited a boom in extraction in the U.S. Abundance of natural gas has enabled many power plants to switch from coal to natural gas. And in the good news, the U.S. carbon dioxide emissions have fallen since 2007. And there's a debate over environmental impact and health concerns versus increased economic benefits and well-paying jobs. Today we're drilling farther offshore than ever before. 35% of oil and 10% of natural gas extracted in the U.S. today comes from offshore sites in the Gulf of Mexico and Southern California. And deep offshore drilling is boosting oil and gas production. In 2008, Congress lifted a moratorium on offshore drilling and opened up most of U.S. coasts for drilling. The public's reaction to the Deepwater Horizon spill forced Obama to backtrack, and he canceled drilling permits until new safety measures were devised. This spill happened in 2010 because of faulty equipment, and it allowed natural gas accompanying an oil deposit to shoot up a well shaft and ignite on a British petroleum platform off the Louisiana coast, killing 11 workers. The platform sank, emergency shutoff systems failed, and oil began gushing out of the broken pipe and onto the ocean floor at a rate of 30 gallons per second. British petroleum engineers tried one solution after another, but the flow of oil and gas continued out of control for 3 months, spilling roughly 4.9 million barrels. That's 206 million gallons of oil. BP's Cont'd well, where the accident took place, lay beneath 5,000 feet of water. The deepest wells in the Gulf of Mexico are now twice that depth. Here we can see some pictures of the devastation caused by that large spill. Countless animals died. Coastal marsh plants died, leading to erosion. Fisheries were devastated. People lost jobs. Tourism suffered. And the economic and social impacts will last for years. Melting ice is opening up the Arctic. Today all eyes are on the Arctic as global climate change melts the sea ice that covers the Arctic Ocean. New shipping lanes are opening, and nations and companies are jockeying for position hoping to stake claim to oil and gas deposits that lie beneath the sea floor. Offshore drilling in the Arctic waters, however, poses severe pollution risks. Frigid temperatures, ice flows, winds, waves, and brutal storms make conditions challenging there. If a spill were to occur, icebergs and storms and cold and wintertime darkness would hamper response effort. The risks from expansion into Arctic waters became clear in 2012 to 2013 when the Royal Dutch Shell's Kulloch drilling rig ran aground while being towed south from Alaska in a winter storm. Damage to the rig raised fresh questions as to whether Arctic Ocean drilling can be conducted safely. We're now exploiting new fossil fuel resources such as oil sands, oil shale, and methane hydrate. Their net energy values are low because they're expensive to extract and process, and extracting of them can consume large volumes of water and devastate landscapes and create pollution. And combustion of these fossil fuels is likely to emit more greenhouse gases and pollution than our regular fossil fuel combustion of oil, coal, and gas. Oil sands are becoming a major fuel source and a focus of debate over our energy future. Much of the world's oil sands underlie a vast, thinly populated region of boreal forest in northern Alberta, Canada. It's a low-quality fuel requiring a great deal of energy to extract and process, and with rising oil prices, mining oil sands is profitable. Unfortunately, to extract these resources, companies must clear vast areas of forest and dig enormous open-pit mines, miles wide and hundreds of feet deep. The immense volumes of water used become polluted and are piped to gigantic reservoirs where the toxic oily water kills waterfowl. The Syncrude Company's wastewater reservoir near Fort McMurray, Alberta, is so massive it's held back by the world's second largest dam. To sell its oil, Canada looked south to the United States. TransCanada Corporation built the Keystone Pipeline to pipe diluted bitumen 2,200 miles to Illinois and Oklahoma. TransCanada then proposed the Keystone XL extension, a two-part project consisting of 1. A southern leg to get oil from Oklahoma to Texas refineries for export overseas, and 2. A northern leg cutting across the Great Plains to shave off distance and add capacity to the line. The Keystone XL pipeline proposal met opposition from people living along the route who were concerned about health, environmental protection, and property rights. It also faced nationwide opposition from advocates of action to address global climate change. Pipeline proponents argued that the Keystone XL project would create jobs and guarantee a dependable oil supply for decades. They stressed that buying oil from Canada, a stable, friendly, democratic neighbor, could help reduce the U.S. reliance on oil-producing nations with authoritarian governments and poor human rights, like Saudi Arabia and Venezuela. Unfortunately, it still can cause more deforestation, despite the fact that it can provide more jobs. Protesters and political debates regarding the expansion have been ongoing since 2008. The science behind the story in our chapter is discovering the impacts of the Gulf oil spill. Many researchers have helped and continue to help assess and monitor the impact of the Deepwater Horizon oil spill, where 62,000 barrels of oil leaked per day. They're using underwater imaging and aerial surveys and shipboard water samples, and researchers track the movement of the oil that spilled. There in the bottom we can see a diagram of that spill. Researchers continue to conduct a wide range of scientific studies to determine the long-term impacts. From burning all these fossil fuels, emissions pollute air and drive climate change. Carbon dioxide is released from land into the air and is driving changes in global climate and may become the greatest impact of fossil fuel use. The emissions cause severe health problems like cancer and irritation. Technology and legislation can help to reduce pollution, but we have to get our legislators in the know about all of this. Clean coal technologies aim to reduce air pollution from coal. Clean coal technologies are technologies, equipment, and approaches to remove chemical contaminants while generating electricity from coal. Scrubbers can be used to chemically convert or remove the pollutants. Coal that contains lots of water can be dried. Gasification is a process in which coal is converted into cleaner synthesis gas called syngas, which can be used to turn a gas or steam turbine. These technologies have reduced pollution, but clean coal is still a dirty way to generate power. Can we capture and store carbon? Even very clean coal releases greenhouse gases. Carbon capture and carbon storage, also called sequestration, captures CO2 emissions and converts the gas to a liquid and stores it underground or in the ocean. Currently, the U.S. Department of Energy is teaming up with 5 energy companies to build a prototype of a near-zero emissions coal-fired power plant. The $1.65 billion Future Gen 2.0 project aims to design, construct, and operate a power plant that burns coal, produces electricity, captures 90% of its carbon dioxide emissions, and sequesters the CO2 underground. The project, located in Illinois, plans to pump carbon dioxide more than 3/4 of a mile underground beneath layers of impermeable rock. If this showcase project proceeds, it could be a model for a new generation of power plants. At present, carbon capture and storage is too unproven to be the central focus of a clean energy strategy. We do not know how to ensure that carbon dioxide will actually stay underground once injected there. Injection might in some cases contaminate groundwater supplies or trigger earthquakes. And injecting it into the ocean could further acidify the waters. Fossil fuel extraction has mixed consequences for local people. Oil companies do provide jobs for millions. 107,000 people work in the Gulf of Mexico just alone. But more people work in tourism, service jobs, and in fishing jobs. Economic booms often prove temporary, and residents are left with a polluted environment once it's all done. And pollution from shale gas drilling creates external costs like having to find drinkable water when water becomes contaminated. Citizens in developing nations don't benefit from drilling. Corporations pay off the governments, and few environmental or health regulations exist, and many people still live in poverty without water or electricity. An Ecuadorian court fined Chevron $9.5 billion for environmental and health impacts. A U.S. court issued an injunction to stop payment. The dependence on foreign energy affects the economies of nations. Nations importing fossil fuels are vulnerable to supplies becoming unavailable or too costly, and seller nations control those prices and can cause panic. Hurricanes Katrina and Rita in 2005 destroyed offshore platforms, causing oil and gas prices to spike. The politically volatile Middle East has the majority of oil reserves, causing a constant concern for U.S. Following the 1973 oil embargo, the U.S. enacted policies to reduce its dependence on foreign oil. U.S. policies to reduce dependence on foreign oil include establishing a 1-month emergency stockpile of oil, cap the price of domestic producers, how much they could charge. They funded research into renewable energy sources. They enacted conservation measures. They urged secondary extraction at old oil wells. And they called for development of more domestic sources. Many want drilling in the Arctic National Wildlife Refuge, but drilling won't help much, and it'll destroy the nation's last wilderness. The U.S. imports more oil from non-Middle Eastern countries. We need to minimize our use of dwindling fossil fuels. Energy efficiency is the obtaining a given amount of output while using less input. It results from technological improvements. Energy conservation is the practice of reducing energy use, and efficiency is one way toward conservation. And we can extend our non-renewable energy supplies by being less wasteful and reducing our environmental impact. The United States uses far more energy per person than people in most other nations, though the United States has cut its energy intensity in half since 1950. Personal choice and efficient technologies are two ways that we can conserve. We can choose to reduce energy consumption, like driving less and turning off lights, and buying more efficient machines. And we don't have to decrease our quality of life. We can still reduce energy use and also save money. Energy-consuming devices can be made more efficient, like cars and power plants. They lose 2/3 of energy as waste heat. The U.S. has become more efficient, but we can do a lot better. Cogeneration is excess heat produced during electrical generation and can heat buildings or produce other power. It can double the efficiency of a power plant. Improvements can reduce energy to heat and cool buildings, like passive solar, insulation, plants, and roof color. Appliances have been re-engineered to increase efficiency, like savings on utilities exceeds the appliance costs. Automobile fuel efficiency is key to conservation. The OPEC oil embargo of 1973 caused increased fuel conservation, but it didn't last. Without high prices and shortages, there was no incentive to conserve. Government research into alternative energy then decreased, and speed limits increased. Policymakers did not raise the corporate average fuel efficiency, or the CAFE standards. Low U.S. gas prices do not account for external costs, and low fuel taxes reduced incentives to conserve. CAFE standards mandate higher fuel efficiency in cars, and fuel efficiencies fell from 22 miles per gallon in 1984 to 19.3 in 2004. In 2007, Congress mandated that cars must get 35 miles per gallon by 2020. I can't wait for that to happen. I wish I had that right now. The rebound effect, it cuts into our efficiency. Increased efficiency is offset by increased energy use. For example, a person who buys a fuel-efficient car chooses to drive more, thereby erasing the gains made by efficiency. Conservation could save 6 million barrels of oil a day, and conserving energy is better than finding a new reserve. It decreases health and environmental impacts while extending our access to fossil fuels. And along with conservation, we still need energy from somewhere. Nuclear power is free of the air pollution produced by fossil fuel combustion and thereby offers us a powerful means of combating climate change. Yet, nuclear power's promise has been clouded by nuclear weaponry and the dilemma of radioactive waste disposal, and the long shadow of accidents at Chernobyl and Fukushima. As a result, public safety concerns and the costs of addressing them have constrained nuclear power's spread. The U.S. generates the most electricity from nuclear power, but only 20% of U.S. electricity comes from nuclear power. France gets 75% of its electricity from nuclear power. Nuclear energy is the energy that holds together protons and neutrons in the nucleus of an atom. We harness this energy by converting it to thermal energy inside nuclear reactors, facilities that are contained within nuclear power plants. This thermal energy is then used to generate electricity by turning turbines with steam. The reaction that drives the release of nuclear energy inside nuclear reactors is called nuclear fission. It's the splitting apart of atomic nuclei. In fission, the nuclei of large heavy atoms like uranium and plutonium are bombarded with neutrons. Ordinarily, neutrons move too quickly to split nuclei when they collide with them, but if neutrons are slowed down, they can break apart nuclei. Each split nucleus emits energy in the form of heat, light, and radiation, and it also releases neutrons. These neutrons, 2 to 3 in the case of uranium-235, can bombard other nearby uranium-235s and results in self-sustaining chain reactions. An uncontrolled chain reaction can cause an explosion, but nuclear power plants control fission. A moderator is a substance like water or graphite that slows the neutrons bombarding the uranium. It allows fission to begin in the nuclear reactor, and excess neutrons can be soaked up. Control rods are a metallic alloy that absorb the neutrons. They're placed into the reactor with the water-bathed fuel rods, and they're moved into and out of the water to control the rate of the reaction. Uranium's atoms are radioactive, and they emit high-energy radiation as they decay into daughter cells. Uranium ore is uncommon, and it's finite, meaning it's non-renewable. Over 99% of uranium occurs as uranium-238, and it does not emit enough neutrons for a chain reaction. It must be processed, enriched into 235. So, uranium-238 is formed into pellets and then put into fuel rods. After years in a reactor, depleted uranium is then replaced. The spent fuel can be reprocessed, but that's expensive, so it's disposed of as radioactive waste. There are currently 436 operating nuclear power plants in 31 nations, listed below. Nuclear power helps us avoid emitting 2.5 billion metric tons of carbon dioxide per year. Power plants pose fewer health risks from pollution and are actually safer for workers than coal-fired plants. And less uranium needs to be mined, which then damages less land and less environments. But the disposal of the waste is challenging. If an accident or sabotage occurs, the consequences are absolutely catastrophic. It poses the possibility of catastrophic accidents like the 3 Mile Island in Pennsylvania In 1979, that was the most serious accident in the U.S. and was due to human error and a mechanical failure. And a meltdown occurred. Coolant water drained from the reactor. Temperatures rose inside the reactor core too high, melting the metal, surrounded the fuel rods, released radiation that was trapped inside the containment building, and the cleanup cost billions and took years. In 1986, there was an explosion at Chernobyl in the Ukraine. It's the most severe nuclear power plant accident that's ever occurred and was due again to human error and an unsafe design. For 10 days, radiation escaped while crews tried to put out the fires, and more than 100,000 residents were evacuated. 19 miles of surrounding landscape still remain contaminated yet today, and the accident killed 31 people directly. Still others today are having effects from it. The Fukushima problem on March 11, 2011 was a 9.0 magnitude earthquake that struck Japan and caused an immense tsunami, killing 2,300 people, and flooded the Fukushima Daiichi nuclear plant. Without electricity and the use of control rods, the uranium fuel overheated, and seawater was used to flood the reactors, but still 3 reactors had full meltdowns. Radiation was released at levels equal to Chernobyl's, and trace amounts then were detected around the world. The problem with these is that this can be global pollution. Thousands were evacuated, and restrictions were placed on the area's food and water. And radioactivity is still being released today. Long-term health effects are still not known. This disaster could have been prevented, and the generator should not be put in basements. Despite safer designs, accidents and human errors still occur, and older plants need more care and become less safe. Radioactive materials can be stolen and used by terrorists, especially in poor nations. Hundreds of former nuclear sites have gone without adequate security for years. The U.S. is buying up some of the radioactive material and using that material to produce power. Waste disposal still remains a challenge. Even if nuclear power was completely safe, we still have the radioactive waste to worry about. That waste is radioactive for thousands of years. The waste is held temporarily in cooling water or steel casks, and the U.S. stores 70,000 metric tons of high-level waste in temporary sites. Over half of U.S. citizens live within 75 miles of temporarily stored wastes, and these sites are vulnerable to terrorist attacks. Nuclear waste managers want one storage site for all waste so that it alone can be heavily guarded. The U.S. stores nuclear waste at more than 120 sites in the 39 states, shown below. Here we can see where Minnesota stores its. Waste storage at the Yucca Mountain in Nevada. This place was chosen to store waste, and $13 billion was spent on its development, and President Obama's administration ended the support for it. So the waste will remain at its current locations. Yucca Mountain was selected because it's remote and unpopulated and has a deeper water table and isolated aquifers, and it's on federal land and can be protected. Concerns over waste disposal, safety, and costs have slowed nuclear power's growth. It's enormously expensive to build and maintain and operate, and then to ensure the safety of nuclear facilities as well. And decommissioning plants is even more expensive. Plants have aged faster than expected, and they serve less than half their expected lifetimes. The costs to generate electricity are higher than from coal and from other sources. Governments must subsidize nuclear plants, and Some people are advocates for more nuclear power with safer reactors. In conclusion, fossil fuels have helped build our complex industrialized societies, but we're now approaching a turning point in history. Fossil fuel production will begin to decline. We can encourage conservation and alternative energies, or we can wait until the stores are depleted. Nuclear energy showed promise, but had high costs and public fear that stalled its growth. So we need to turn to renewable energy sources.